In the early 1980s, for those of us lucky to have computers, it was commonplace to compare your computer system to those of your friends and classmates. At that time, the comparisons were largely around the availability and gameplay of hit games. How did the graphics of the latest hit game compare between the Commodore 64 and the Atari 800? Did your machine support 4K and only allow limited levels and graphics? Or were you blessed with a 16 or even 48K machine? What could you even do with 48,000 bytes of memory? At an actual processing level, none of us kids knew or cared how to compare the 6502 versus the Z80 versus the 6809, and what in the world even was a TMS 9900. I only knew that my friend's Commodore disk drive loaded as slow, if not slower, than my Atari tape drive. Hello, I am the Mighty Pez. In this video, we will be comparing the performance of two of my 1980s retro computers using a well-known algorithm, the Sieve of Eratosthenes, as implemented using standard basic interpreters from these systems. So please, join me for this showdown to determine who is the king of the performance hill. As a subscriber to Byte magazine in the 1980s, I read an article in the September 1983 issue that discussed comparing the relative performance of various computer systems. Later, as a computer science student analyzing algorithms, I became interested in all things having to do with comparing both performance and optimal use cases of various systems, software, circuits, and chipsets. I never forgot the article over the next 40 years. The article was revisiting a previous 1981 article that proposed comparing the relative performance of various computers and their high-level languages. They chose an algorithm called the Sieve of Eratosthenes to benchmark the systems. And before we concern ourselves too much with the suitability of a single algorithm to provide a valid comparison between all of our childhood systems, we acknowledge that the performance of any system has as much to do with the quality of the compiler or interpreter as it has to do with the computer itself. Ignoring this caveat, I will go full steam ahead with my plan to ultimately compare all my home computers with this single algorithm. For science. In this video, I will compare my Apple IIe to my Atari 800 XL. Sadly, my intent was to run this comparison on my first computer, an Atari 400. However, that computer decided not to power on. So thankfully, I still have my second computer ever. My plans for future videos are to compare my other systems including Z80, 6809, and even 68,000 CPUs. I will not be implementing improvements to the algorithm or use a more recent algorithm to artificially boost comparison speed. I will, however, make whatever concessions within the various basic implementations themselves, such as allocation of data types or line ordering, if it does not change the algorithm. I will also note my changes to the various listings and describe the performance implications. Finally, my code will be posted on my GitHub page. First, let's start with a quick review of the algorithm from this article. Just a reminder, this is not the best and most efficient method of calculating primes. However, the purpose is to compare the same process across multiple computers. First, we will create a working array to hold our list of candidate values to validate. Second, we flag all values as prime until we go in and mark specific values non-prime. Lastly, we iterate through the array, check to see if we've already validated this number as non-prime. If not marked out, the candidate is actually prime, and we then iterate through the rest of the multiples of that number, marking them as non-prime. I will demonstrate using a subset of the array to identify primes up through 99. First, we notice that each array element I represents a candidate value I plus 3. So the first element represents 0 plus 0 plus 3, or 3. This leads to our first issue. The algorithm will not identify 2 as being a valid prime. Starting with array element 0, prime number 3, we see that it has not been marked out yet, so it is prime. Now we loop through each third element starting at 0, marking them out as being non-prime. The second time through the array, we start at element 1 and have identified 5 as being prime. So we loop through each fifth element starting at element 1, marking them as non-prime. We then follow for element 2, representing the prime value 7. Now we hit element 3, which has already been flagged as non-prime, so we do not continue in that loop, but instead move directly on to element 4, representing prime value 11. I will iterate through elements 5 through 15. After completing element 15, representing non-prime value 33, we notice that there is no reason to iterate any longer, since the next element, 16, plus a step of 35, would be outside of our array. So at that point, all remaining unflagged numbers are indeed prime. Let's use the Google to identify all prime numbers between 1 and 99 to validate our results. As we said, 2 is a known miss. Our algorithm has identified 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97 as prime. So let's begin with the Apple IIe. I have entered the BASIC program into AppleSoft BASIC. I had to make one significant change from the listing, which was to replace the while when loop, which is not supported on any of my machines, with the goto loop. I will begin with the version of the program closest to the 1983 Byte magazine version to get our first benchmark timing. Although we are primarily concerned with the total time taken, I am also tracking the initialization time so that I can analyze changes to the basic code. The article reported a runtime for 10 iterations at 2,806 seconds. Our observed runtime of 5 minutes and 38 seconds would have resulted in a 10 iteration runtime of 3,380 seconds, 574 seconds slower, or 57 seconds per iteration. So what gives? Did my decades-old 2E slow down? Looking back at the original September 1981 article, we see a clue. Although the algorithm is the same, the code has two differences. First, they use the same goto logic I used instead of a while when loop, so that is not the problem. Second, we see a change that hints of a code optimization. The array size of 8190 is assigned to a variable. In AppleSoft Basic, the string of characters 8190 has to be parsed and turned into a numeric value each time it's accessed through the loop. In the 1981 version, which ostensibly the reported timing was based off of, the value was only parsed once when assigned to a variable. From then on, through each loop, we accessed a much quicker integer variable. So I will make this change to the code and rerun the timing. Amazing! That single change took 1 minute off the single iteration runtime. Now we are only 5 seconds off the time reported in the magazine. For our last attempt, we will take advantage of another known optimization, moving our heavily utilized code, especially loops, closer to the top by pushing our one-time initialization code to the bottom. Every time a goto is encountered, it has to search for its target from the start of the program. So by moving rarely used code to the end, each heavily utilized goto will execute faster. Another improvement to the code is replacing the original goto loop from the 1981 version with a for next loop. Due to the way AppleSoft Basic is implemented, I needed to skip the loop if the starting value k already exceeded the ending value x. This was not needed in the Microsoft Basic for Atari version, as that version would not enter the loop in this state. This latest improvement allowed us to reduce the single iteration runtime by 78 seconds, giving us an overall performance improvement of 30% from the reported runtime in the magazine and a whopping 53% improvement over our first unoptimized run. Next, we will run the initial code on my Atari 800 using Microsoft Basic for the Atari. I chose the Microsoft version of Basic for the initial comparison, as the original Atari Basic was well known for its lack of performance. In a future video, I will compare the Atari Basic version for speed. For the initial run, there is only one change to the code. I declared the variables with the dim command, even though I had previously defined the variables with the defint. The reason for this is, when I did not dim the variables, I was having issues with overwriting memory used by other variables. For example, updating the count of prime C or enter count K would cause the array F to become truncated. The first run of the Byte magazine version of the code on Microsoft Basic for the Atari showed a 17-second improvement over the run on the Apple II. That gives us a baseline. Now we will apply the same optimizations that we learned while tuning the code for the Apple version and see if we get the same magnitude improvement. As in the case of the AppleSoft version, we were able to replace two gotos with a for next loop. The difference being that we did not have to test for variable k exceeding x prior to the loop. Before we analyze the numbers, let's compare the base clock speed of our two contenders. The Apple IIe has a clock speed of 1.023 MHz, whereas the Atari 800 has a clock speed of 1.78. So naively, one may expect a 74% improvement in performance running the identical task. And one may not be surprised that the algorithm based on an unoptimized 1983 Byte magazine version gave the Atari a measurable edge. However, applying the same functional improvements to both machines gave the Apple a clear edge. We will definitely have to give this win to the Apple IIe. So, what did we learn from all of this? Comparing machines using a single metric such as clock speed or a single algorithm is mostly useless. Vendors and fans of various systems could rightfully pick and choose the features and software that shone the best light on their system of choice. Due to market pressures in the 1970s and 80s, manufacturers were many times under pressure to rush products to market, sometimes resulting in deficiencies such as suboptimal performance. Atari Basic, I am looking at you. Or in some cases, poor hardware decisions, naming no names. In many cases, rushed software design, both in the basic language as well as games, might shine a poor light on hardware, whereas well-designed software makes the system appear to be stronger. In the end, the real goal was to provide a feature-rich platform for the end user, and although the Atari was no slouch, the Apple II wound up having a longer lifespan and more overall unit sales. And no matter the outcome, my first system was an Atari 400, and I will stand by it as the best computer line at the time. Thank you for watching this video.